Second, since we can also take a revisit, we can also review the spontaneous emission as well. We have the relation between the A21 and the B21 as the emission here, and it is relevant to the mole density of your cavity. And the RSP term is proportional to F2 times 1 minus F1. Okay, it also relevant to the reduced density of state. Also the transition matrix element and another bunch of constant. Now we are not going to derive that again. Just pure effort. Anyway. But we can get a quick insight if we compare the spontaneous emission rate and the radiated emission rate by the population term. This term is F2 times 1 minus F. RSP is proportional to F2 times 1 minus F1 or F2 minus F2 F1. And the RST, stimulated emission, is proportional to F2 minus F1. Since F2 is smaller than 1, it's a number between 0 and 1. So F2 minus F2 F1 definitely larger than F2 minus F1. So if you are not trying to do anything, this term has always a stronger population factor. The stimulation will always be difficult. So no matter you pump it really hard or pump it really low, the spontaneous emission rate should prevail. That don't make the stimulation prevail if you pump it really hard. So what should we do if we only want we want the things to lay easier? We have to try to suppress, either enhance ISP or suppress ISP. Yeah, you can try to do something to make the stimulated emission stronger somewhere else than the F2 than the population factor, or trying to make the ISP prohibited in your structure. It's all allowed strategy. So we have some, since we see that the A21 is directional to the more optimal density. So this is the first we can manipulate here. For most of the cases, the cavity is large. The mole density is very narrow. It's always one mole need to the other mole. So it's actually very difficult to manipulate your density of mole. However, if we make the cavity very small, to make it a micro cavity, a cavity whose dimension is close to its wavelength, then the most basic, the spacing become mole to mole, start to deviate, become wider. Then, if you design a small cavity with a mole to your interested wavelengths, then such term will going up because you are caring about a small volume and a small region in the spectrum, a small area in the spectral region. That will make the RSP enhanced. and it can be enhanced by a value called the Purcell factor. Purcell factor is something like this. The derivation is also pretty physical, and I didn't ever try to do that. Anyway, we can just follow the result. The Purcell factor, that means how the spontaneous emission rate is enhanced. If it is 1, that means no enhance. It's just like the spontaneous emission rate in the bulk material. But if you make the cavity small and fit the wavelengths, your interesting wavelengths, the Purcell factor tells you your spontaneous emission rate will be enhanced so many fold, and the thing is constant. So it's relevant to a term called Q over Vp. Q is the quality factor. Vp is the mole volume. Yeah, since when the mole volume is small, you are trying to cut a small cavity, the mole volume will decrease. The definition I also skip. It's not that will be too away from this guy. But there's an important quality factor. What does quality factor mean? Quality factor means while the light is circling around your cavity for 1 round, how many energy remain? So it's defined by the optical energy stored to the optical energy loss. So let's make a simple sketch. Let's consider a big disk, and the light is propagating like this way. It's going internal direction, internal reflection. That's the light starting from a starting point. And at each path, there might be some loss. So the energy, the photon will be leaving this cavity during this circle. And if after 1 bounce, if it return to its same phase, it created more. Okay, so for such a mode, you must have some optical energy leaving this cavity, and some optical energy still within the cavity after the 1 round of the optical feedback. So, if no energy is lost, the light is 100% still kept in such cavity, then you have a quality factor goes to infinity. It's a very high quality factor. So the spontaneous emission rate will be strongly enhanced. But there's a logical trap. If all the optical energy is kept within such cavity, how can you measure that? Yeah, I say this is the infinite. You have a quality factor of almost infinite. That means all the light will circling around this cavity. So that will makes it very difficult to measure. So there's another way to measure that to evaluate its 4 wavelengths half maximum, 半高宽. That will be, this quality factor will be also equal to mu over delta V. So if you get a spontaneous emission pretty sharp, so your delta V will be small. To some degree, you will start approaching the stimulated emission. If you have a small cavity with a spontaneous emission with a very high quality factor, this mode will also be your lacing mode. Then the if the definition between spontaneous emission and the stimulated emission becomes blurred, two things will start eventually become one thing. But that's also a very interesting topic for the people doing microcavity laser. They are always competing. How can they make a so sharp microcavity, a very good microcavity, to make their Q factor super high? And it becomes a competition. It says that I can make it 2,000. Okay, no, it says I can make it 10,000. Another says I have a data code 2 million. But the problem, how do you have a spectrum with so good the resolution? Okay, that's another story. And then another way to think about the cavity effect is to do the opposite. If we do some rearrangement of the material, so we make the optical mode density is 0 at some wavelengths, then the spontaneous emission doesn't happen in such an area. The light cannot enter this area as 2. Yeah. Things is not happening, you cannot make anything. So this comes to an important concept called the photonic crystal. Photonic crystal makes a change of periodic condition. That makes the light has a 100% destructive interference at some spectral range. And we call it the photonic crystal band gap, photonic crystal band. And that area with no allowed frequency is called photonic crystal band gap. So if we have a material doing photonic crystal, we can let the spontaneous emission 100% suppressed with such structure. It will have so many potential complications. Potential complications. But we have more potential applications. The most earlier photonic crystal already appeared in the market. It's called the DFB laser. Distributed feedback laser. That makes your quantum wave non-continuous. I have some gain here, gain loss, gain loss, gain loss. We do that with common processing and make the reflecting index different along the epi wafer. So the processing is rather easy while the wavelength is long. So it has actual applications here. And it have a very strong application in with something called wavelength tunable lasers. That's also we will teach that in lecture 13 or 12 anyway. So this the simply one come to popular use since 1970s. It's nothing new. But if we're trying to do that in a 2-dimensional way, it becomes something hot topic. Still hot, but not so hot recently. But it's very hot in the from 2000 to 2015. Yeah, I think at least for this thing is a super hot topic. In the second, if you can do that in the 2-dimensional way, the current most useful application is to make a hollow fiber. What does hollow fiber mean? In optical waveguide, we have line bouncing through and back, like this. And we have N2, N1, and optical mode, something like that. But no matter, well, even when you have a total infraction, but however, the alpha, the loss, optical loss, is never 0, even it's below the band gap. There's some additional mechanism, something like a radial scattering, or something like a free carrier scattering, something like that. It could be very, 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 very low, but never really reach zero. Yeah, we can say almost zero for some application, but never reach zero. So it comes a concept called hollow fiber. That means we are doing a fiber projection like this, but we have nothing inside. But you might be questioning, the air has N is equal to 1. The reflecting index is low. How shall we keep the line in the center? The original concept is if I didn't put any material inside, there's no material, there will be no loss. Then the wave will be propagating much longer than the real fibers. So the idea is that we make photonic crystals at the edge. So the whole process is like that. We make a photonic crystal with a pattern in the with nothing in the center, and so many holes with decided the dimension at the edge. Then we make a big size one. Then we pour the hot glass like a liquid through the mesh. Then it will form and eventually stretch that. So it's starting with a big cross section, but since it's cooling and stretching, so the total size will shrink eventually. So this is also technology. 所以那就像在拉那个软糖一样，它先用一个比较粗的 cross section 把 photonic 做好，然后呢倒入那个很滚烫的石英液体石英了以后，然后在冷却的过程中开始拉伸它，所以整个的 structure 就开始，然后你要说的尺寸对，它就会对于某些波长的光旁边形成 photonic crystal。哦，这种有在卖，这个有商品化，这可能是有 photonic crystal 相关的产品，真的目前有真的进入市场应用的东西，但这个就还蛮贵的，而且你可以看这个东西其实是蛮脆弱的，像这个中间都是薄皮，对，所以是不是真的有用？这也许你可能要问问看其他做通讯的老师。So there's another term called spontaneous emission factor, because while you are, even you have a cavity, you have some light, but the light needs to be generated by the semiconductor itself. Now we don't have light exciting from the outside. So let's consider a semiconductor laser like this. For example, this is gas, and this is our gas. Our gas. And we have a quantum well in gas. In the center. And while we inject some carrier, surely we would emit in all directions with equal probabilities. Yeah, since it's a dipole. Yeah, well, I don't know what's the phase or orientation. Each one is independent even between itself. But some of them, if the emission angle is right, it might coupled into an optical mode of your laser. So beta ht can be defined. First, so the denominator is the total spontaneous emission rate. Since we know that spontaneous emission can happen while a mode is coupled to it, but not all the mode is about your laser. Since while laser you only have few modes, it's usually at the peak of the gap. The few modes is actually contributing the laser. So that means it's actually lot of spontaneous emission doesn't help the final lasing. So how effective the spontaneous emission really build the lasing action is called the spontaneous factor. That means the spontaneous emission rate of the lasing mode divided by total spontaneous emission rate. So if I have a large cavity, that means the cavity is the size is much larger than your wavelength. Most of the semiconductor lasers, edge-emitting lasers, since your length probably hundreds of micron, and the width is 20 or 30 micron, the size, the cavity size, is much longer than your lasing wavelength. But so you have so many allowed optical mode inside that. But only the few one will achieve lasing. I will show you why in the second part of there's so many optical modes, but eventually there will be only few, one or two will really be your lasing mode. Okay, so since this number is limited, probably less than 5. But if you have a cavity with a large cavity, that means your beta SP will be small. Most of spontaneous emission light is not relevant to your lasing behavior. But however, if we make this number smaller, that means most of the most of extreme case is that every spontaneous emission mode will last. They will make a small cavity, which has only one mode, and that one mode also match the lasing mode. So there will be no difference between the spontaneous emission and the spontaneous emission, the stimulated emission. So this is the curve, is the LL curve. The x-axis is the pumping density of the pumping density could be optical pump. So optical pump is the megawatt per centimeter square, and the output power is this case. So in the larger cavity, the line curve looks like this. At the beginning, the output power for a specific mode, the output power is low. Because it has so many modes, I'm also measuring a specific mode. So the total output power will be low. But after lasing, because such mode length, it will dominate the optical behavior in the cavity, it becomes high. Okay, so this part is the spontaneous emission. This part is the stimulated emissions. But if your cavity is so low that your cavity is small, so your beta, the spontaneous emission factor, increases. Then that means a high portion of the spontaneous emission rate to a specific mode will be approaching to the limit of the lasing mode. So you eventually, if it goes to 1, spontaneous emission will be equal to stimulated emission. That's also a topic that people trying to do the microcavity laser will compete. How large is my spontaneous emission? Some people will say, I get a LL curve that I cannot fit the spontaneous emission. Because if you say I have a spontaneous emission equal to 1, it is very dangerous. That's why people will be very unhappy about your claim. It is very strong. That means you're trying to make a cavity. You cannot all the light, the first photon you throw out is a lasing photon. Well, that is a pretty ambitious claim. So people will say a more conservative tone. I get the LL curve that I cannot find the threshold carrier density. Yeah, probably it's here and small, but because the power is too weak, so I cannot measure that. So that's it. Anyway. Okay, so beta SP is also an important factor while building your laser. Yeah, if you make a great laser, you the small volume, you will get a high spontaneity, you will get a high percell factor, FP increase, and the beta SP also increase. Then eventually, the difference between the spontaneous emission and the student emission no more exists. Yeah, so that's a pretty advanced topic in the common semiconductor laser research.